Hello, welcome to my first YouTube video. Today we're going to be going over a basic Hohmann transfer problem where we have this orbit A, right, a smaller orbit, and then we're trying to go into this orbit B, a second larger circular orbit. And we have satellite A here and satellite B initially positioned here 60 degrees apart. So if we look at the problem, figure P7.11 shows two satellites moving in concentric coplanar orbits around the Earth. Satellite A is a 300 kilometer altitude circular orbit, and satellite B is in a 700 kilometer circular orbit. At epoch T0, satellite B is 60 degrees ahead of satellite A, as depicted in the figure. Determine the earliest epoch time T1 such that a Hohmann transfer delivers satellite A to the 700 kilometer orbit so that satellites A and B occupy the same position on Earth, aka it's a rendezvous. Let initial epoch time T0 be 0. In addition, determine the total delta V for the Hohmann transfer rendezvous. Okay, so the first thing that we need to do is determine the radiuses or the radii of these two orbits, A and B, right? So our radius of A is going to be the radius of the Earth plus the altitude here, right? And so I've kind of laid out some equations here that you can put into your backpack of formulas that you should know for transfers and orbits and all this. So starting off, we'll find the radius of A equals the altitude of A plus the radius of the Earth. And that's going to be 300 kilometers plus our radius of the Earth is 6,378 kilometers, giving us a total of 6,678 kilometers, right? So that's RA, RB. We do the same thing, altitude of B plus RE equals 700 kilometers plus 6,378 kilometers, which gives us 7,078 kilometers. All right. And so now that we have the radiuses of satellites A and B, we know that since it's a Hohmann transfer, we're going to have an elliptical transfer going from orbit A to orbit B, right? And to do that, we have an ellipse. So we're starting off like this, and then we do our first burn here, and it puts us in this ellipse. And then we do our second burn here to put us into this circle. But this ellipse here, right, we have to find out some information about it. First thing we need to know is the semi-major axis, right? So we can go ahead with our equation. We have semi-major axis equals the perigee plus the apogee over 2. And so we see here our perigee, or our closest point in the orbit, is going to be the same thing as this RA, and the apogee, or the farthest point in this orbit, is going to be the same as RB. So we can go over here, and we can say that that's the same thing as R orbit A plus R orbit B over 2 equals 6,678 kilometers plus 7,078 kilometers over 2, and we get A equals 6,878 kilometers. All right. Now, if we want to know the time that it takes to go from this orbit here to this orbit here, we have to find the transfer time. And so we know that this elliptical orbit here is going to have a period of t, and since we're making 1/2 of our orbit here, the transfer time is going to be 1/2 of the period. So we go over here and we look at, all right, the period for an ellipse is 2 pi times the square root of a of the transfer cubed over mu, and mu is the gravitational constant. So we have mu for the Earth is 398,600 kilometers cubed per second squared. And that's going to be a number that you'll probably end up memorizing. So we find t period equals 2 pi times the square root of at cubed over mu, which equals 2 pi times, go back here, 6,878 kilometers cubed over 398,600 kilometers cubed per second squared, and that all equals 5,676.81 seconds. Right? So then our transfer period, or our transfer time, is going to be 1/2 of our period, which will equal 2,838.41 seconds. All right. Now that we know how much time the transfer takes, let's try and figure out how far satellite B will move in that amount of time in radians. To do this, we need to find the satellite B's angular velocity, right? Because we have satellite B moving from here, and the angular velocity will be constant because it's moving in a circle. So to do that, we need to find the velocity that it's moving at. And if we go here, velocity for a circle equals square root of mu over r. So we can say VB equals the square root of mu over RB equals square root 398,600 kilometers cubed per second over RB, which we found to be 7,078 kilometers. And that will give us a velocity of 7.50435 kilometers per second, right? And then just going back to very general dynamics here, we know that omega equals V over R, right? That should be something that you're very familiar with. So omega B equals VB over R equals 7.50435 kilometers per second over our radius, RB, 7,078 kilometers, which gives us an angular velocity of 0.00106 radians per second. All right, now we can find how much the true anomaly of satellite B changes during our transfer time, right? Because we have, again, we have satellite A going from this first orbit over to the second orbit, and we want to find how much time or how much angle this satellite B is moving, because we want to eventually have satellite A reach the same point as satellite B. All right, so that's going to equal true anomaly theta B equals angular velocity of B times the time, right, transfer time, which we found earlier. So we have 0.00106 radians per second times our transfer time of 2,838.41 seconds and that will give us 3.00938 radians. So that's how much satellite B is moving over that time. Okay, so now let's think about what necessary change in true anomaly between satellite A and satellite B needs to be. So to do this, we need to remember that the Hohmann transfer moves a full pi radians, right? Goes back to here. We have from here to here, Hohmann transfer is going to be half of this ellipse, so it's pi radians, right? So we have our change in true anomaly is equal to pi minus FB equals, or sorry, not FB. Well, it doesn't matter. You can use F, you can use theta. Minus theta B equals pi minus 3.00938 radians, which equals 0.132213 radians. So this is the desired separation between satellite A and satellite B. Now for the last step of this problem, we need to calculate how long we need to wait until satellite A and satellite B's separation is this change in true anomaly value. So to do that, we need to first find omega A, or the angular velocity of A. So first off, we start with our velocity A, right? We're doing the same thing we did for the first orbit. And so we do VA equals mu over RA equals square root of 398,600 kilometers cubed per second squared over RA, which was 6,678 kilometers. And that should give us a velocity of 7.72584 kilometers per second, which should make sense, right? Our velocity of this inner orbit is greater than the velocity of our outer orbit because this satellite is closer, so it has less potential energy, so it needs more kinetic energy. All right, so there's our velocity A, and then if we go back to omega A equals VA over RA, we get 2584 kilometers per second over RA, 6,678 kilometers equals 0.0011569 radians per second. All right. Okay. So now we can go ahead and find an equation that describes the difference in true anomaly between satellite A here and satellite B here. So you can see that we're starting with an initial difference in true anomaly of 60 degrees, or pi over 3 radians, and we have satellite A moving at a constant angular velocity here, satellite B moving at a constant angular velocity here, right? They're both circles. Okay, so we have our change in true anomaly equals our initial difference in true anomaly, right, our 60 degrees, plus the difference in angular velocity times time. So if we look, we know that we can expand that out. So that's the same thing as pi over 3 plus omega b minus omega a times time. Okay, so we've already solved for our difference in omega, and we know WB, and WA. So we can go ahead and solve for t equals delta omega minus pi over 3 over WB minus omega A. If we plug that in, we get 0.132213 radians minus pi over 3 over our omega b, 0.00106 radians per second, minus 0.0011569 radians per second, and we'll end up with a time of 9,464.87 seconds. So this is the time that we need to wait in order for satellite B to be in the right position, so that when we do a Hohmann transfer of satellite A, it'll intercept with satellite B, right? Because if we did a Hohmann transfer from here, it wouldn't end up intercepting here. So we have to wait until it's the right time to do our Hohmann transfer, so that it'll intercept here when we do our orbit, right? So another part of this problem is finding the total delta V for this mission. So this is actually pretty easy, since we already have the velocity of orbit A and the velocity of orbit B, and we have the semi-major axis of our transfer orbit. So we know from our equation that V of transfer orbit at point A equals 2 mu over RA minus mu over A, semi-major axis of our transfer, equals square root 2 times 398,600 kilometers cubed per second squared over RA, which was 6,678 kilometers, minus mu again, and I'm not going to write the units this time, and then we have A, which we calculated to be this, right, all over the square root, and we get a velocity of 7.83736 kilometers per second. And then we can go ahead and find the velocity of the transfer orbit at point B. And so it's going to be the same equation. Same equation, just with a different radius, right? We're using RB, all right, over AT. And we have 2 times 398,600 over RB, which is 7,078 kilometers, minus 398,600 over our semi-major axis A, right? And that's going to get us a velocity of, 7.3944 kilometers per second. So now we have all of our velocities, right? If we go look up here, we have our velocity of this orbit, we have the velocity of this transfer point for the ellipse, we have the velocity of this orbit, we have the velocity of this transfer point from this ellipse, right? So we have all our velocities. So now we can go ahead and calculate our final difference in velocity, right? So we have delta V initial burn is just our change in velocity. So we have VTA minus VA. And I'm not going to plug in the numbers. You already have these from our problem. So it's going to equal 0.111522 kilometers per second. And then we can find delta V final burn equals VB minus VTB equals 0.109912 kilometers per second. So that's the difference in our second burn. And then if we want to find our total delta V throughout the entire mission, it's going to be delta V initial plus delta V final, right? Because we're just adding up the velocities from those two burns, and that's going to give us 0.221433 kilometers per second. So that's going to be the total velocity change that you'll have going on this, this transfer orbit here. All right, so that's all I have. Thank you for watching.